Let's have a quick look at concentration and how concentration affects the rate of a chemical reaction. Firstly, what do we actually mean by concentration? Well, let's take a couple of beakers here and we'll look at the two extremes. When we're talking about concentration, at one end we have dilute, so we could have a dilute solution. At the other end we have a concentrated solution. Concentrated, right. What is the actual difference between them? Well, let's say we had the same amount of water in here and we dissolved a certain salt into this. Let's talk about copper 2 sulfate. Maybe we're making a copper 2 sulfate solution. Okay? Dilute solution means that you don't have many solute particles per unit volume, right? So we've got the same amount of water here, but in the dilute solution, we will not have many copper 2 sulfate particles. In the concentrated solution, it's the opposite. We have got lots and lots. So in this one, we'll just keep tapping on my screen and drawing lots and lots of dots. So this solution is more concentrated. Okay, so a dilute solution, few solute particles per unit volume, and a concentrated solution, we have many solute particles dissolved. Okay, so there's the general difference. If this salt that has been dissolved, if the solute is able to give colour to the solution, then the concentrated solution will be a darker colour. Okay, so here we have a darker red, whatever was dissolved for the concentrated solution, and then a lighter colour, more of a pale pink for the more dilute solution. This image shows it as least concentrated. Well, a different way to say least concentrated is most dilute. Remember? So we've got the concentrated end and we've got the dilute end. All right, so we're just, it's all talking about concentration, but usually we don't talk about the least concentrated, usually we say the most dilute, because that's the other end of the scale. So let's look at an actual photograph here, very simple solutions. These are solutions of brown sugar. Now the one on the left is a dilute solution, it is lighter in colour. The one on the right is the concentrated solution, it's darker in colour. There was more sugar dissolved in the one on the right. Okay, cool. So let's look at how this affects reaction rate. Here we have 3 test tubes. They each have hydrochloric acid in them, and then a piece of magnesium ribbon was added. So the magnesium ribbon was the same length in each. The magnesium ribbon was 3 centimeters in length. 3 centimeters, 3 centimeters, 3 centimeters. Remember, when we're doing a prac, it's important that we only change one variable. We weren't changing the amount of magnesium, so we had to keep it the same. We were changing, in this case, the concentration of the solution. Now, what we had was in the first test tube, we had 2.5 mils of 2 molar HCl, 2 molar hydrochloric acid. In the next test tube along to the left, we had twice as much, we had 5 mils, and we still had hydrochloric acid, but in this case it was only 1 molar acid, so half the concentration. Remember, molar stands for mole per litre, we're talking about the molarity. Okay, that's the concentration of a solution, the molarity. In the first test tube, the leftmost one, we actually had 10 mils, and again we had hydrochloric acid, but again the concentration was different. In this case we had only half molar acid. Okay, now here's a point to consider. I said that we need to keep everything constant except for the one variable that we're changing, right? And the variable we're changing is concentration. You can see we had 0.5 molar concentration, we had 1 molar, and we had 2 molar concentration. So there are our concentrations. And yet when you look at this image, you might think, wait, hang on, we've got different amounts of acid. And we can't do that. We can change the concentration, but everything else has to be the same. That's why we had 3 centimeters magnesium ribbon and 3 centimeters and 3 centimeters. We kept the amount of magnesium the same. Surely we have to keep the amount of the acid the same as well. Well, yes, of course we do. And we actually have. Now, it may not look it, because this on the right looks like less acid than we have in the middle, which is less than we have on the left. At first glance, granted, it appears like we have different amounts of acid, but let's actually work out how much acid we have. N says number of moles. Okay, so we're talking the number of moles of the HCl. That's the acid particle in there. Remember, most of the acid is actually just water molecules anyway, but we've got some hydrogen chloride dissolved, and so dissolved in water solution, that's what makes it an acid, hydrochloric acid. But the number of moles, and let's write that, N stands for the number of moles. The number of moles is given by, well, there are a couple of formulas you can use. In this case, we're going to use concentration times volume. Okay, so when we're dealing with solutions, moles is equal to the concentration times the volume. Now, let's work out the number of moles of the first test tube, the one on the left. Okay, our volume is 10 mils, but remember, we work in litres, so it's actually 0.01, okay, when we're talking litres, and our concentration is 0.5. Okay, so let's do that. Our concentration, what did I say? I said 0.5, that's our molarity, our concentration, our volume is 10 mils, which is 0.01 litres. Now, when we do this calculation, we're going to move our decimal from this number. We're just going to move our decimal 2 places, and it's going to be 0.005. And we're working in moles. The symbol for the mole is the mole. Okay, so N stands for moles. N says I'm talking about moles, much like S would be talking about displacement and V for velocity. N says you're talking about the moles, okay? And the unit is the mole. So there we go. In the first test tube, the one on the left, we had 0.005 mole. Remember, moles is actually the SI unit, so it's a nice, good official unit to use. It's the SI unit for amount of a substance. Okay, the amount of stuff, right? The amount of a substance you have. Okay, the SI unit for the amount of stuff is the mole. So we have 0.005 mole of acid particles in that first test tube. Okay, all right, grand. Actually, let's label. This is test tube number 1, the one on the left. What about test tube number 2? Well, the number of moles of the HCl in the second test tube is equal to concentration times the volume. Now, the concentration, let's go back here. Wait, where is it? There it is. The concentration was 1 molar and our volume was 5 mils. So our concentration is 1 and our volume is 5 mils. But of course we work in litres, which is 0.005 of a litre. And we can easily times that by 1 and we're going to come out at 0.005 mole. And what do we notice? It's the same amount. Now, we could hopefully see the pattern already, but just in cases, let's do the third test tube. Number of moles, and remember we're talking of the acid particles there is equal to volume times concentration, or concentration times volume. It's multiplication, doesn't matter which you do first. But the concentration in this case was 2. Let's just remind ourselves of that. Here we go. We have a concentration of 2 molar, and our volume was 2.5 mils. So concentration was 2, our volume was 0.0025, because we do our calculations in litres. And when we do that, 25 times 2, well, that's a 50. So there we go. We're going to have a 5 in the answer instead of a 2.5. And we're actually going to come out with the same number, right? The same result. So in the first test tube, we actually had this amount of acid particles. In the second one, we had the same amount of acid particles, and in the third test tube, we actually had the same amount of acid particles. So yes, granted, when you first glance at the test tubes, it does look like we actually had different amounts of acid. But as we've just seen, we've just calculated that actually we had the same amount, right? The moles is the amount of stuff you have, and of the acid particles, the HCl molecules, we actually had the same amount. So we looked at changing the concentration for this one, even though we had the same amount of acid particles. Now, that was a bit of a long-winded way to just say, yeah, we kept everything else the same. What we notice on this one when we actually do the prac is that the magnesium ribbon dissolves, firstly, because we've put a metal into acid. We're going to dissolve the metal and get bubbles of hydrogen gas, which you can see in 2 of the test tubes. You actually can't see much going on in the third test tube because it's nearly all gone. Here's a little bit of magnesium ribbon there. It has nearly all dissolved. Now, how long did it take to dissolve? Well, in this case, with the most concentrated solution, it took 55 seconds. Now, the middle test tube, the magnesium did all dissolve, but it took a lot longer. It actually took 2 minutes 40 seconds. And let's not mix up the way we write things. If we're doing minutes and seconds, let's do it like this. There we go, minutes and seconds. The first one, well, I should say the most concentrated, because they were all done at the same time, but the most concentrated took 55 seconds to dissolve the magnesium ribbon. The middle concentration, the 1 molar acid, that took 2 minutes 40 seconds. And the most dilute concentration of the acid, the most dilute solution, that actually took 8 minutes 30 seconds to completely dissolve the magnesium ribbon. So we've timed it. That's great. It's always good to have quantitative data, but in terms of qualitative data, just observing, you can't really see much in that, but it's lots of hydrogen was given off, so it's really quite bubbly, right? It's quite a vigorous reaction. In the middle example, we've got a bit less hydrogen, and in the example on the left, we have even less hydrogen, so less bubbles. The reaction was less vigorous, okay? That's why it took longer to complete. So might be a bit hard to tell in the photos, but anyway, we have the numbers data. Here we go, right, in terms of minutes and seconds. So the most concentrated, the reaction went quicker. The least concentrated, the reaction went slower. Now, why? What's the deal? Why would the reaction proceed quicker in a more concentrated solution? Well, it comes back to that very first diagram that we had. Remember, concentrated solution, more solute particles. Well, the solute is one of the reactants, okay? In this case, we weren't actually looking at copper sulfate, were we? We were looking at magnesium ribbon into HCl. So let's write this reaction equation. This is going to make magnesium chloride. There we go, 2 chlorides. Okay, we're going to need 2 of these, and we're going to make some hydrogen gas, H2. Hydrogen gas is a diatomic molecule. So there's our balanced chemical equation, and so we're making this H2 gas. That's why it was getting all bubbly. But in the more concentrated HCl solution, we had more HCl particles. Remember, every dot is a particle, right? An HCl particle, if you like. So more particles means we're going to have more collisions of those particles with the magnesium ribbon. Okay, let's draw our magnesium ribbon. Here we go, 3 centimeters of it, 3 centimeters of it, roughly. Okay, so the same size. Now, what we have is, let's change color, how many acid particles are slamming into the magnesium ribbon on the left in the dilute solution? Well, we've got one here, we've got one here. This guy's pretty close. This guy's kind of close-ish. So let's say 4, right? How many in the concentrated solution? Well, we've got one here, we're up to 3, 4, 5, 6, 7, 8. So you're pretty close, so 9, 10. Let's just say 10-ish, right? The point is, more particles colliding. The collision theory tells us that in order for reactants to do their little reactant thing and form the product, they must first collide. Well, we've got more collisions in the concentrated solution. More particles there, right? It's more concentrated, so there are more particles there. And that means more collisions. And if you have more collisions, you have more effective or successful collisions. And that's what gives us the faster reaction, the amount of successful or effective collisions. So there we go. We've seen in a more concentrated solution, we have a higher number of collisions, and therefore we will have a higher number of successful collisions or effective collisions, and that means the rate of reaction will increase. The reaction will proceed at a faster rate, and therefore take less time, which it did, only 55 seconds. So there we go. By increasing the concentration, we can increase the rate of a chemical reaction.
Don't forget to hit the like button. Yeah. And subscribe too. It's up here. And here's another video.